Now, we said the only thing that's variable on each one of these is the side chain. And so the side chain is really generally where each amino acid gets its flavor, gets its properties from, because everything else about it is simply going to be, we'll see, in the service of getting them to connect to each other. So the side chains are where the action is. The side chains are how we decide how it's going to behave. So if I look at these three right here, what sorts of functional groups do you see? Pause the video and go ahead and let me know what you're seeing here, or let yourself know what you're seeing here and jot them down. Okay, so if we are ignoring all the all the pieces of this that are the NH3 and the COO minus right here, then all we're really seeing for the rest of it are alkanes, right? And so we refer to these as non-polar amino acids. They are ones that have for their side chains specifically non-polar groups. And so we'll start to fill out this worksheet here as we go along. And what the worksheet tells us here is that the non-polar amino acids are almost entirely made up of alkanes. Now, if we think about alkanes, they're not the most interesting functional group from a functional point of view. They don't do a whole lot. And so in terms of their chemistry, what I would expect, physically, I expect them to be oily. I expect them not to play well with water. I also expect them to be hydrophobic. And I expect them to be not terribly chemically active. There's not a lot that alkanes do besides bursting into flames. And just by virtue of being an organic compound at all, that's a threat for a lot of things here. So yeah, not a whole lot of interesting chemistry here. If we want some more interesting chemistry, or at the very least some more interesting interactions with water, we need to make our move over to amino acids with slightly different functional groups involved. Note quickly here, if you take a look at the chart of amino acids that I've provided on our website, you'll see that these are not the only three. There are a bunch of nonpolar amino acids. Take a look at the functional groups that are on those and convince yourself that they are things that you wouldn't expect to give you a whole lot of polarity. Now, these functional groups, these R groups, are a little different. So again, I'd like you to pause the video. If you need to consult the list of functional groups to help you with this, by all means do so. But identify which functional groups you observe here in threonine, cysteine, glutamine, and tyrosine. All right, as you unpause the video, we see alcohols here in threonine. We see aromatic alcohols here in tyrosine. I've got an amide showing up here in glutamine. I've got cysteine over here that's got some thiol in it. We see a lot of functional groups that for the most part would give you some polarity. In fact, in all but one of them, they would provide you some hydrogen bonding. And so we call these polar amino acids. And again, we've got a variety of possible functional groups. Alcohols have been listed in here, amides, thiols, phenols. Basically, as we said, things that can hydrogen bond mostly. Not exclusively, but mostly. We're going to have two more groups of amino acids coming up in a little bit, but these polar amino acids we would expect to be hydrophilic. We would expect water to want to interact with them. So if we start to think about a molecule that has certain amino acids that are nonpolar and hydrophobic, certain amino acids that are polar and hydrophilic, you can start to imagine that a protein might look like a big version of the micelles that we've seen already, something where we bury those nonpolar groups and expose the polar stuff. We also have a couple of other interesting things. If you remember back to our discussion of pKa during Monday's lecture videos, tyrosine and cysteine contain a pair of amino acids that are actually weakly acidic. Tyrosine, this phenol, remember, had a pKa of about 10. The thiol and cysteine would have a pKa in the vicinity of 7. And so these are groups that in the right conditions might actually show up with the H plus removed and a negative charge. They might appear as their own conjugate base instead. Threonine over here is vulnerable to oxidation as a secondary alcohol. This could actually lose H's from here and here and become a ketone. So if we needed to undergo some actual oxidation reduction chemistry, threonine might be a good thing to involve. Cysteine can do something a little special that we talked about from this diagram, which is the formation of a disulfide bond. If I've got two cysteines side by side, I can pluck those H's off and make a bond in between. It looks a lot like an oxidation version of a condensation reaction, right? In condensation, I remove H and OH and make a bond in between to link two molecules together. In disulfide formation, I'm taking away two H's instead and doing this. So those are some of the things that the polar amino acids might be able to carry out. If we move on to the other groups, two of these are named very obviously, aspartic acid and glutamic acid. In this case here, what we see exclusively are carboxylic acids. And the interesting thing about acidic amino acids is what's going to happen to them based on what we discussed on Monday. If I have acidic amino acids, things with carboxylic acids on them, remember that the pKa of a carboxylic acid is somewhere around 4 or 5. The pH of a typical fluid in the body is somewhere around 7.4. So the pH is much higher. That means I'm under much more basic conditions than the pKa, which remember, if my pH is equal to pKa, I'm at the break-even point. I will have equal amounts of the carboxylic acid and its conjugate base. If I've got a pH that is more basic by 3.5 pH units, I'm going to mostly see its conjugate base. And you'll even notice that on these things right here, what that ends up meaning is that I've got a negative charge. And you'll see here that all these amino acids have even shown the carboxylic acid that is common to all of them, shown as COO-. But that will also be the case for the carboxylic acid up top. It will also be deprotonated under physiological conditions. If we want to look at the flip side of that, we've got a variety of functional groups, I believe 3 amino acids that contain bases. There's one more, histidine, that you'll see on your table. But in each of these cases, we've got amines present. And so what do amines do? Well, coming back here to how they handle this sort of thing, well, amines have a pKa in the vicinity of 9. Again, physiological pH about 7.4. So in this case, I'm at a more acidic pH than that break-even point, which means I'm going to almost exclusively see the conjugate acid of these amines. And so in actuality, what I have here are ammoniums and carboxylates in these things when I'm under physiological conditions. And so you'll notice that the amines tend to take on a positive charge. They pick up an H+ when this happens. And so if you're looking for places where a protein could generate a charge to perhaps attract two groups to each other, this is going to be the way it's done. Now to finish this off, let's give you one you haven't seen so far here, asparagine, and have you try to classify this based on the functional groups present. Pause the video, take a moment, give it a try, and when you come back, we'll see what the right answer is. Okay, now that you're back, hopefully what you've determined here as you examine this structure is that in order to classify it, I'm going to ignore all of this. Don't even think about it. That's going to make the backbone of our protein as we go forward. This is the part I want to look at, and the big thing we see here is the presence of an amide. Now, crucial thing, an amide is polar, but because of the presence of that carbonyl group, it is not basic. So if you happened to say that this was a basic amino acid because you saw the nitrogen, you need to make sure you look at what the nitrogen's attached to. A nitrogen just attached to any old carbon, that'll get you an amine. But if it's attached to a carbonyl, it's an amide, and it acts a little differently. Just like acids, carboxylic acids, look kind of like alcohols with a carbonyl, and that changes whether they're able to dissociate. Same thing's true with amides and amines. Amide, no dissociation, not basic, it's polar. Amine, able to pick up an H+, it's basic. So this would be a polar amino acid. We would expect its behavior to be in line with the other ones we observed, tyrosine, cysteine, threonine, etc. Okay? Now, as we move to our next lecture video, we're going to start assembling these things, and we're going to begin by building this tripeptide, which will have the abbreviation DVC, into one single protein. See you there.